In this video, we're going to look at the structure and reactivities of aldehydes and ketones, nucleophilic addition mechanisms, and the process of reduction. We'll start off by looking at aldehydes. As you'll have seen in topic 5, looking at alcohols, aldehydes have the suffix -al, so an example would be butanal. And the functional group of an aldehyde is the C double bond O at the end of the molecule, so the H coming off the carbon can be considered part of this functional group as well. When drawing the skeletal formula for an aldehyde, it's acceptable to show the hydrogen as part of the skeletal formula. This is because, like we've just said, the hydrogen is essentially part of this functional group, so by showing the hydrogen on the skeletal formula for the aldehyde, it makes it really clear that this is an aldehyde that you've drawn. Ketones have the suffix -one, so an example would be butanone. Similar to aldehydes, the functional group for a ketone is the C double bond O, but this time it's in the middle of the molecule rather than at the end of it. You need to know two chemical tests for aldehydes and ketones. The chemical tests work on the basis that aldehydes can be oxidized, but ketones can't be oxidized. If you need to recap on why aldehydes can be oxidized and ketones can't, check the work you did on topic 5, looking at alcohols. The first test is to add Tollens reagent to your sample of an aldehyde or a ketone. Tollens reagent is a colourless solution of silver nitrate dissolved in aqueous ammonia. If you're answering an exam question or writing up a practical about Tollens reagent, it's acceptable just to call it Tollens reagent. You don't need to explain what it's formed of. After you've added the Tollens reagent, you need to heat it up. If an aldehyde is present, a silver mirror will form. If a ketone is present, there will be no reaction. And here we can see what they look like. So from test A, that's a negative reaction, therefore a ketone was present. B and C are both positive results. If you do this practically yourself, you're more likely to see the results from test B than C. Typically, the concentrations of the chemicals we use in A-level laboratories will not give you a full silver mirror. You'll get quite a murky, light brown or grey solution. If you or your teacher uses higher concentrations of the chemicals, you may be able to see the full silver mirror as shown in sample C. Using failing solution is the second test for aldehydes and ketones. Failing solution is a blue solution of copper-2 ions dissolved in sodium hydroxide. As with Tollens reagent, you can just call it failing solution. You don't have to go into detail as to what it contains. Again, like Tollens, you'll need to heat it up once you've added it to your sample. And then in the presence of an aldehyde, you'll form a brick red precipitate. If a ketone is present, there'll be no reaction. And again, here are some pictures showing those results. So we can see our initial blue solution of copper-2 ions, and then our brick red precipitate formed if we have a positive test result. Aldehydes and ketones can react with nucleophiles through a nucleophilic addition mechanism. We're going to look at the general example for that mechanism now. We're going to start off with an aldehyde. It'll be exactly the same for a ketone, apart from you'd have another R group, another carbon group, rather than a hydrogen. We've also got our nucleophile, making sure to draw the lone pair and its negative charge. If we look at the partial charges for the molecule, oxygen is more electronegative than carbon, so oxygen will have a partial negative charge. Therefore, carbon will have a partial positive charge. So the first of our mechanism is going to involve the lone pair of the nucleophile attacking the carbon here. You don't need to draw the partial charges on a mechanism in an exam question unless the question specifically asks for you to draw the partial charges. So the first step shows our curly arrow going from the lone pair on the nucleophile to the carbon on the aldehyde or ketone. The second step involves the electrons from one of the bonds in the carbon-oxygen double bond being moved up to the oxygen. So we're breaking the double bond and replacing it with a single bond. This will give us the intermediate structure shown here. As before, we've broken one of the double bonds. That means the oxygen now has a lone pair and a negative charge on it. We'll look at the reagents involved for specific reactions shortly, but these will usually be done in dilute acid, meaning there are H+ ions in the solution as well. What's going to happen next is the lone pair on the oxygen will attack the H+ ion to form an alcohol group. This is the final step in the mechanism, and this is what nucleophilic addition looks like. Typically, with aldehydes and ketones, we use the nucleophilic addition mechanism we've just looked at to produce chemicals called hydroxynitriles. Before we look at the mechanism to form hydroxynitriles, we need to look at what these molecules are. As you've probably guessed by the name, they contain both the hydroxy or alcohol group and the nitrile group. So for example, this would be a hydroxynitrile. We've got the nitrile group here, the CN group, and the alcohol or hydroxy group. This molecule would be 2-hydroxypropane nitrile. The reason we use hydroxy rather than ol to denote the alcohol group is because if we used ol, we would have two suffixes. We'd have to try and have the nitrile group and the ol put together, so instead we name the alcohol group using its prefix hydroxy. There are 3 carbons in the chain, remembering that the nitrile carbon is part of the chain, which is why this is propane nitrile. You could be asked to name more complex hydroxynitriles. So this molecule still being a hydroxynitrile as it's got the alcohol group and the nitrile group. So this one would be 2-hydroxy, 3-methyl butane nitrile. Because we've got 4 carbons in our chain, we've got the hydroxy group on carbon 2 and the methyl group on carbon 3. Hydroxynitriles are formed by reacting an aldehyde with potassium cyanide. So let's look at what chemicals would have to react together to form 2-hydroxypropane nitrile. Well, we'd need to react ethanol with potassium cyanide. Now, what's really important to remember with forming hydroxynitriles is that we're adding a carbon to the chain because we're reacting it with the cyanide group. So if we want to form propane nitrile having 3 carbons in the chain, we need to start off with an aldehyde which has 2 carbons in the chain because we're adding a carbon when we add the nitrile group. This is different from most mechanisms you'll come across during A-Level Chemistry, where the number of carbons at the start is the number of carbons at the end. So you need to remember when forming hydroxynitriles that you're going to add a carbon to the chain. So this would form 2-hydroxypropane nitrile. You need to be able to write this in displayed form, word form, and structural form as well. So here you can see the completed equation using structural formula to show the reaction between ethanol with potassium cyanide to form your 2-hydroxypropane nitrile. The conditions for this reaction would need to have dilute acid present as well, because remember the dilute acid is what allows us to add the H onto the alcohol group at the end of the mechanism. We're now going to look at a worked example. So we need to write the equation and draw the mechanism for the formation of 2-hydroxybutane nitrile. The first step in a question like this is to draw out our product so we can work out what chemicals will need to react together. So we're going to start off by drawing out 2-hydroxybutane nitrile. We now need to decide which 2 chemicals to react together. Remembering that because we're adding a carbon, because we're adding a nitrile group, we can see, as highlighted in green, we'd need to start with something with 3 carbons, so we'd need to start off using propanal. We're going to react the propanal with the potassium cyanide and form 2-hydroxybutane nitrile. So we've written the equation, now we'll need to draw the mechanism. We'll start off by drawing the propanal and making sure that we remember the lone pair and the negative charge on our nucleophile, in this case the cyanide ion. The first step is for the cyanide ion to attack the carbon, so making sure our arrow starts at the lone pair, finishes at the carbon. And the second step is breaking the carbon-oxygen double bond and that electron pair from the bond being pushed up onto the oxygen. This will give us the intermediate structure shown on the screen now, remembering to include the lone pair and the negative charge on the oxygen. The conditions for this reaction is that it occurs in dilute acid, so we're going to have H+ ions present as well. So the final step is the lone pair on the oxygen attacking the H+ ions to complete the mechanism. In the last topic, we looked at optical isomers and what enantiomers are. The nucleophilic addition mechanism we've just looked at can produce a mixture of enantiomers or a racemate. We need to be able to explain why this mechanism produces a 50-50 mix of enantiomers or a racemate. Double bonds, for example carbon-carbon double bonds, or the carbon-oxygen double bonds we've just been looking at in aldehydes and ketones, are planar. This means they're flat. So I've tried to draw this to represent the C double bond O as a flat part of the molecule in the plane of the screen. It's important to remember we need to specify that the double bonds are the planar part, not the entire molecule. So the rest of your molecule could have its tetrahedral structure, for example, but the part with the double bond in will be planar. In the nucleophilic addition mechanism, the nucleophile can attack from above or below the double bond. In this case, it's attacking from below. Each attack is equally as likely, and each attack will produce a different enantiomer. So for example, if this nucleophile attacks from below, it's going to push the 3 groups around that carbon upwards, which is going to form one enantiomer. Alternatively, as shown in blue, instead the nucleophile could attack from above and push those 3 groups downwards, which would form the opposite enantiomer. This of course requires each of the groups around the what will be a chiral carbon to be different, but assuming they are, whether the molecule is attacked from above or below the plane will produce a different enantiomer. So we can summarise this, or write it out as an exam answer, by saying the nucleophile can attack from above or below the molecule, each attack is equally likely, and each attack will produce a different enantiomer. Since each attack from above or below is equally as likely and each one produces the opposite enantiomer, this means we're going to form a racemic mixture, because we'll have a 50-50 mixture of both enantiomers. Let's look at a worked example, a kind of question you might find in an exam. So the products of the reaction between propanal and potassium cyanide under weakly acidic conditions are present as a racemic mixture. Explain why. We'll start off by drawing the mechanism so we can see what reaction will take place. So we've drawn propanal and our nucleophile, remembering its lone pair and negative charge. We'll complete the mechanism by drawing the first steps, so the arrows from the lone pair to the carbon and the C double bond O up to the oxygen. We'll finish off the mechanism by drawing the intermediate structure, showing the lone pair and negative charge on the oxygen, and showing the oxygen attacking the hydrogen, which is present from those weakly acidic conditions. So we can now see that the mechanism involves attacking a planar C double bond O group, which means we can write the answer we've just practiced a moment ago. We can use this as a little checklist to make sure this is the answer we're going to give in terms of why a racemic mixture will be formed. So we've used a nucleophilic addition mechanism, we've attacked a planar C double bond O, and the attack has occurred at a chiral carbon. Writing our answer out fully, we can say the attack of the Cn- nucleophile occurs at a chiral carbon. The planar C double bond O group has an equal chance of being attacked from above or below the molecule. And as each attack produces a different enantiomer, and each attack is equally as likely, a racemic mixture will be formed. We're now going to look at what reduction is. Reduction is the opposite process to oxidation. So in oxidation, we increase the number of bonds to oxygen. We go from alcohols to aldehydes, aldehydes to carboxylic acids, or alcohols to ketones. In reduction, the number of bonds to oxygen are decreased. So we're going to go from being an aldehyde or a ketone back to being an alcohol. In oxidation, we used an O in square brackets to represent the oxidizing agent, the chemical we use in this process. In reduction, we use a H in square brackets to represent the reducing agent. The reducing agent we're going to use is sodium borohydride, NaBH4. Reduction occurs through the nucleophilic addition mechanism, what we've looked at earlier on in this video, using a H- ion as a nucleophile. This is the only time throughout A-level chemistry where you will use a H- ion. Usually it's a H+ ion, but the reducing agent will generate a H- ion. That's because the NaBH4 is essentially a positive sodium ion, BH3, and a H- ion. The reduction of an aldehyde or a ketone, if we had a R group rather than the H here, needs two equivalents of reducing agent, because we're essentially adding two hydrogens onto the molecule and will form an alcohol. It will form a primary alcohol if we're reducing an aldehyde, and a secondary alcohol if we're reducing a ketone. Let's look at a worked example for what the reduction of propanone would look like. So writing out the structural formula in the form of an equation, we can see that we've got propanol plus two equivalents of reducing agent. Remembering we can write the reducing agent, the sodium borohydride, as a H in square brackets, and this will form as propan-2-ol. So again, we're going from a ketone to a secondary alcohol. The mechanism is just a nucleophilic addition mechanism we've looked at throughout this video. So we're going to start off by drawing the ketone and our nucleophile, which in this case is a H- ion, remembering to include the lone pair and the negative charge. As before, the first step will be for the lone pair on the nucleophile, the H- ion, to attack the carbon, and the second step being the breaking of the carbon-oxygen double bond to form a single bond. We'll need to draw our intermediate structure again, showing the lone pair on the oxygen and the negative charge, and finish off the mechanism by showing the lone pair on the oxygen attacking that H+ ion, reforming the alcohol group.